Welcome back to the deep dive. Today we're going to focus on that single moment where high-speed precision manufacturing, well, it either succeeds or it fails. And it often comes down to an engineering detail that seems so small, so trivial, that a lot of people just ignore it. It's the connection between the spindle and the cutting tool. Just think about the machines you work with. You've invested a ton of money, multi-axis machines, advanced controllers, spindles that can hit, 15, 20,000 RPM, and yet you might be consistently losing accuracy. Or maybe your surface finishes are degrading and you're just burning through thousands of dollars in expensive tools, and it could all be because of a tiny, tiny flaw in the setup.
It really is the ultimate paradox, isn't it? We solve these huge problems of speed and control, but we get undone by the simplest mechanical interface, the tool holder. Our sources for this deep dive, they really zero in on why the industry workhorse, the standard BT holder, is fundamentally flawed for high-end work. And more importantly, how these advanced systems, often called BBT or Big Plus, they solve that flaw with just a millimeter of engineering brilliance.
Right, and that's the central question we're digging into. If you're relying on just taper contact, you are dealing with a standard and very deliberate 3 mm gap. So our mission today is to really understand the physics of that gap, how dual contact systems get to a perfect 0 mm closure, and why that tiny change can boost the rigidity of your entire setup by up to 30%.
That's the primary nugget right there. It's recognizing the limits of relying only on the taper. The classic BT system, it has one point of contact, which leaves the tool assembly vulnerable. The BBT system completely changes the game by using dual contact, the taper, and the spindle face to eliminate that instability for good.
Okay, so let's unpack this. Because if you put a BT holder and a BBT holder side by side on a bench, they look almost identical. They use the same foundational geometry. So let's start there. What's the fundamental standard that both systems are built on?
Okay, so we have to start with the global standard, which is the 7.24 taper ratio. This is it's a non-negotiable industry standard. It's a very specific, very shallow cone angle. And what that does is it ensures a kind of self-locking wedge fit.
And that's the same across all the sizes, right? Whether you're using a little BT30 or a huge BT50 for roughing.
Exactly. The diameter of that taper shank, it decreases by 7 millimeters for every 24 millimeters of axial length.
Right.
And that geometry is, well, it's sacred. It's what provides the radial alignment to center the tool perfectly.
But that's where the catch is, isn't it? In the classic BT holder, that perfect geometry comes with a built-in sacrifice.
It does. The standard BT design says the tool holder relies exclusively on that taper wedge. The flat face of the holder, the flange, is designed very carefully to make sure it never touches the machine's spindle nose.
Why? Why would they enforce that separation?
It's a fail-safe, really. If the flat face hit the spindle before the taper was fully seated, the tool would be misaligned. It would wobble.
Oh, okay.
So by guaranteeing the 3 millimeters of separation, the engineers made sure that only the taper is taking the alignment load. The drawbar pulls it up, the taper locks, and the gap it stays there.
So the 3 mm gap isn't a flaw, it's a feature, a necessary byproduct of a single-point connection system. So then how does the BBT system manage to keep that same 7.24 taper, which is so crucial for compatibility, but also get rid of that gap?
This is where we move from standard engineering to, well, really clever engineering. The BBT system, which was pioneered by Big Showa, it just changes the rule. It says we must have simultaneous contact. And they do this not by redesigning the taper, but by tightening the tolerances on both the spindle face and the holder, flange, to an incredible degree.
That sounds really, really hard to pull off. I mean, if you grind them just a tiny bit off, you risk the face hitting first, and then the whole thing is useless.
That's the core challenge. And the solution is dynamic, not static. The BBT system is engineered around the actual material science of the spindle itself. They calculate for the what's called the elastic deformation of the seal.
Elastic deformation. So you mean they're actually using the machine's own flex?
Precisely. When the drawbar pulls that BBT holder up, first, the 7.24 taper makes contact. That gives you the initial alignment.
Yeah.
But as the drawbar keeps pulling with thousands of pounds of force, the mouth of the spindle expands outward. We're talking a microscopic amount, just a few microns.
And that tiny expansion is just enough to create the space?
Yes. That slight outward flex allows the super precise face of the holder to finally make contact with the face of the spindle. The result is a perfect, simultaneous 0 millimeter contact at both points. They've basically weaponized the machine's own physics to get a locked connection that the static BT design could never, ever achieve.
That is genuinely fascinating. It's not just a wedge anymore, it's a fully locked structure. So for you listening, that's the whole difference right there. BT is taper only with a 3 millimeter gap. BBT is taper plus spindle face for a 0 millimeter, all achieved through force and material flex.
Hmm.
So now we go from elegant engineering to, well, brutal high-speed reality. Why does that 3 millimeter gap or that taper-only connection become such a massive weak point when you start pushing the machine?
It all comes down to one thing: centrifugal force.
Okay.
When you are spinning a tool holder at 12 or 15 or 18,000 RPM, the forces are just enormous. And that force causes the mouth of the spindle to expand radially. It opens up kind of like a bell.
And when that spindle mouth opens up, even a tiny bit, that perfect wedge fit of the BT holder is gone.
It's compromised, exactly. The fit loosens. And the drawbar, which is always under tension, it immediately yanks the holder deeper into that now expanded paper. This movement has a name. It's called pull-in.
And how much pull-in are we talking about here
Yeah.
in the real world for a precision job?
It might only be 20 or 30 micrometers, but in precision machining, that's a catastrophe.
Right.
If you're milling a pocket and your Z-depth tolerance is plus or minus 10 microns, that dynamic pull-in completely destroys your accuracy. The tool tip actually moves deeper mid-cut, which leaves steps, ridges. You end up with a scrap part.
So the BBT system solves this by physically bracing the tool against the spindle face.
Exactly. Because the face of the holder is locked against the face of the spindle, it acts as an immovable stop. That dual support creates a much wider, much stiffer base that just resists that axial movement. It doesn't matter if the spindle mouth expands a bit. That face contact holds the Z-axis position at 0.
And that's really the difference between static and dynamic rigidity, isn't it?
That's the perfect way to put it. Static rigidity is how stiff the machine is when it's just sitting there. Dynamic rigidity is how it performs under load, at speed. And that face contact gives a huge boost to dynamic rigidity. The base acts like a shock absorber, helping the whole assembly just eat up vibration energy. The data is really compelling on this. This dual contact design increases overall spindle rigidity, its ability to resist deflecting under load by at least 20% and often up to 30% over the taper-only systems.
And for the person actually running the machine, the result is obvious, right? Z-axis pull-in is gone, and that huge increase in stability just kills chatter, which gives you a much, much smoother surface finish.
And we should connect that rigidity directly to your operating costs, because this is where the ROI on BBT holders really starts to make sense.
You mentioned expensive tools. If you're cutting something like titanium or Inconel, those high-end end mills can be hundreds and hundreds of dollars a piece.
They're assets, and you have to protect them. The number one enemy of carbide is vibration. Carbide is incredibly hard, but it's also brittle. It just hates chaotic, high-frequency stress. In a taper-only BT system, that microscopic movement, that wiggle in the gap, causes a phenomenon called fretting.
Fretting, can you explain that? What's actually happening to the metal?
Fretting is just localized wear between the holder and the spindle taper. But the real problem is that this micro-vibration travels straight down the tool to the cutting edge. So instead of a clean shearing action, the cutting edge is experiencing constant impacts and vibration.
It's essentially microhammering the material instead of cutting it.
Precisely. And that vibration causes stress. The sharp corners of the end mill are the first to chip off. And once that corner breaks, or the coating fails, heat builds up incredibly fast and the tool just burns out, sometimes in minutes.
And by locking the tool in place with dual contact, the BBT system stops all that rocking and tilting.
It stabilizes the entire system. The cutting edge engages the material smoothly, consistently every single time. And that leads to predictable, even wear. This lets shops push their feed rates higher, which means more material removal. But the big thing is it saves a ton of money. We have sources reporting cases where manufacturers literally doubled the life of an end mill just by switching to dual contact.
Wow.
Yeah. So if you have a $400 tool that normally gives you an hour of cutting and you can get 2 hours out of it, that's an instant 100% ROI on that tool alone.
That's a powerful argument for upgrading. But let's talk about the practical side for someone who already has a huge tool crib full of BT holders. If you get a new BBT-capable machine, do you have to scrap all your old tooling?
And that's the good news. The designers were smart about this. They kept that critical 7.24 taper geometry. So because of that common foundation, BBT and BT holders are generally interchangeable. They'll physically fit in each other's spindles. No danger, no crash.
Okay, that's a relief. But I'm guessing you don't get the magic dual contact benefits just by mixing and matching.
That is the essential caveat, and it's so important for you to get this. You only get the full dual contact, the zero gap, the 30% rigidity boost when a BBT holder is paired with a BBT spindle.
Okay, let's walk through the combinations just to be crystal clear. Scenario 1. I take my old standard BT holder and put it in my brand new BBT spindle. What happened?
It'll seat on the taper just fine. But the flange on that old holder isn't ground to the right tolerance to engage the spindle face. The drawbar pulls it tight, the 3 mm gap is still there, and you're back to standard taper-only rigidity. It works, but you lose the advantage.
Okay, scenario 2. I buy a new expensive BBT holder and I put it into my older standard BT machine.
Same result, different reason. The taper seats perfectly, but the older BT spindle face was never prepared to receive the holder face. It hasn't been calibrated for it. So again, the gap remains. You're still operating on that single point taper connection. And actually, we should add a warning there.
What?
While mixing is okay for general work, using a BBT holder in a standard BT spindle can, over the long term, cause uneven wear on your spindle taper. It's really best to match them for any high-performance job.
This whole deep dive really drives home a key lesson of precision engineering, doesn't it? The solution to a huge performance problem often lies in a tiny, tiny adjustment. The industry just dealt with a standard 3 mm gap for decades, which caused pull-in, fretting, and just terrible tool life.
And the fix wasn't some radical redesign. It was just leveraging the physics of the system, the force and the flex of the steel, to close that gap completely. Eliminating that instability gives you 20 to 30% more rigidity, and it makes sure you get every penny's worth out of those expensive tools.
So what's the big takeaway for you listening to this? It really highlights that sometimes the biggest leaps in capability, they come from finding and fixing the smallest structural element. It should encourage you to look past the big components and ask, where else in my processes, in my connections, my supports, am I tolerating a necessary little gap or instability that, if I could close it, could unlock a whole new level of performance and savings?
That's the lesson. Maximum performance isn't found by adding more horsepower. It's found by eliminating micro movement. Go find the hidden gap in your system.